Okay, Benjamin. Where's Benjamin? Where's Benjamin? Tell me one changing quantity in this situation. What was one changing quantity you came up with? Any? Okay, how do you do defining that quantity? The area. So what's missing from that? So what we did that first week in terms of defining quantities and variables holds all semester long. We get in that habit and we do it. So just to say area, what's wrong with that? It doesn't have to have a unit unless we're doing a variable, right? So just a quantity doesn't have to have a unit. What's that? Yeah, so if you say area, what's missing? What area are you talking about? You know, specificity. You got to be specific when you define quantities and variables. You said area. I'm looking at 5 different areas. I'm looking at 6 different areas up there. The area of the base, the area of one of the sides, the total surface area of the box. There's all kinds of areas you could say. So what area were you thinking, Benjamin? Area of the base. Okay, Brianna.
You said the length of the sheet of paper, the inches?
The length of the original sheet?
Yes.
Okay, Timothy. Where's Timothy? Not here? Oh, tell me another one. You're just thinking? Okay, so what's another changing quantity in this situation? Whoa, that was 3 different things. What do you want? Area of the cutout. Okay. Okay, another quantity. Let's see. John. Another volume of the resulting box. Okay, what else? Is it Nick? No, Eric. Is it Eric?
Yeah.
Another changing quantity in the situation. Height of the box. Nicole. It's another changing quantity here. The weight of the paper. Okay, so the very most obvious one has not been chosen yet. Tell me your name again.
Caitlin?
Caitlin?
The area of the sides?
The total area of the sides? Or just the area of one side or
Area of one side?
area of one side? And do you want a short side or a long side?
Short side.
Okay, we're still missing the most obvious changing quantity here. Yeah.
The length and width of the base.
Okay, so the length of the resulting box. And the width, that's 2 different ones. Width of the resulting box. Okay, still missing the most obvious one. Samantha, do you know what it is?
The length of each cutout?
The length of the side of the cutout, right? Okay, that's plenty. All right, that's plenty to just, and so we can keep going. There's lots of things changing as you change the length of the side of the cutout. All these other things change. Okay, lots of things change. So let's focus on. We're gonna focus on these. Volume of the resulting box. So of course the length of the cutout, volume of the box, height and width, or oops, not the width of the paper. Height of the box, length and width of the box. All right. So the length of the cutout that you cut, and then the resulting length, width, and height of the box, and volume of the box that you get. So that's where we're gonna focus on. Okay, so let's define a variable for the length of the side of the cutout, and we'll use x for that. Let me do this better. All right, how did I do defining my variable? X is the square cutout side length. Rashini. Well, now I need units because X takes on the values, it takes on numbers. So with the numbers, we need to know what those numbers represent. So what's the obvious choice here? In inches. Okay, and then what do we say? Let's let L be the length of the box, and then in inches. W will be the width of the box in inches. H will be the height in inches. And then V will be the volume. And what will the unit of that be? Cubic inches, right? Cubic inches or inches cubed. Okay, so we got 5 variables here. And is it comfortable that those are all, as we change the square cutout side length, all those things change? Do you see that? Okay, so let's just talk a little bit about that. If I increase the size of the square cutout, what happens to the width? What happens to the width? Stevie. So if here's one square cutout, I'm going to increase the side of the square cutout. What happens? Oops. I'm still holding on. I'm going to increase the side of the square cutout length. What happened to the width when I did that? Decreases. Agree with that? What about the length of the box? What do you think? Yeah, decreases too. Okay. What about the height? If I increase the square cutout length, what happens to the height? That increases. How is the height related to the side of the square cutout? Cody, what's the relationship between the height of the box and the square cutout side length? You're Cody, right? Yeah. Okay. Do you know what that relationship is? Too big. So we got the square cutout side length. How is that related then to the resulting height of the box? Can you see it? What is it? So that's that. What's it? The length of the cutout is what? The same as the height. Yeah, they're the same. Yeah. So whatever length you cut out of the square becomes the height of the box. You see that? So x and h, they're two different quantities. They're variables for two different quantities, but they're always equal. Okay. So we do want to distinguish between x and h as two different variables because they have two different meanings. But in this situation, their values are always equal. Okay, now we want to write the the width of the box and the length of the box in terms of the cutout. Did you get to that? Did you have that? Did they have you do that? In what you got to? So here's our width of the box. Can you see on this rendering of it, where is the width? Like how would we show the dimension of the width on this, the flattened paper with the squares cut out? From the red dot, where?
Down to the base of it, so that segment right there.
From there to there?
That distance.
He wants that distance is the width right there.
Just saying, width is the other way.
Going to the right? Tell me when to stop.
Stop.
Okay, he's saying from there to there is the width. Agree? Yep. Okay, so there's our width. That's our width. And can we write an expression, and our side cutout length is that's our side cutout, right? So can we write an expression that gives us that value of W but using X? So can we write an expression that has X's in it that gives us that W? So I want everyone to think about it. Some of you already know it. So we're writing W in terms of X. Somebody tell me your name. Is it Ellis? What's your name? Yeah. Travis. Okay. Last letter, right? Okay. Any ideas? How would you write what that width is using X?
We use 8.5 for the total width of the paper.
Okay, total width of the paper is 8.5.
Minus 2x.
And why are you saying that? Can you explain that?
Because we cut out two cutouts on each side of the paper.
Okay, so you got 8.5 is the total width of the paper. And you want to subtract 2x. So like an x over here and an x over here.
Yes.
And that will leave this width W. So W equals? What do you guys think? That's what he's offering up. Agree with that? Yeah, good. Okay, so then what about so if we want to do the same thing but L in terms of X? All right, but there is someone Ellis, right? Is there Ellis?
Yeah.
Ellis, okay. So now we got this, the total original width of the paper, 11 here. And we're going to subtract off an x here and an x here. And that gives us this, the length of the box, L. Okay. And what about the height in terms of x? The height, Jimmy, what's h in terms of x? Okay. He's asked the question. H equals x. What do you guys think? H equals x? What? H equals x. Agreed? Yep. You got it. Okay. Now let's talk about the volume of the resulting box. So what's the structure of our volume formula? What's the structure of the volume formula? Noah? What is it? Okay, good. So length. So now that we have the width in terms of x, and the length in terms of x, and the height in terms of x, we can write the volume in terms of x. Do it. Everyone do it. Write the volume of this box in terms of the length of the square cutout. meaning we're going to have just an expression with x's in it that will generate the volume of the resulting box. Okay, so is it Christian?
Yes.
Tell me, how did you get your volume formula in terms of x? Looks like you got your calculator. It doesn't really have anything to do with your calculator because we're just writing a formula, right? And everything you need, I've written on the screen. So if volume is length times width times height, and we've got length in terms of x, width in terms of x, and height in terms of x,
Okay.
how could you rewrite the volume?
11 minus 2x times 8.5 minus 2x times x.
That's it. So it's the length times the width times the height. So what does that formula do? It takes a value of what? TJ, it takes a value of what and gives what?
Take the value of x and gives you volume.
And what was x again?
X is the cutout.
Right. Okay, so we just did part E on page 82. You flip the page, on page 82 we just did E. So look at F and G. So notice it's in F and G. It says use your formula from part E to represent the volume of the box when x is 0.5. Okay, so notice it didn't say find the volume. It said use your formula to represent. So this is something you're writing out, you're representing using the formula what the volume would be, but you're not calculating the volume. Do you understand? Using the formula. Okay, so tell me. A little bit louder. What'd you say first? Sorry. 8.5. Good. Times. Okay. How do you do? Yeah. So this is totally valid. Okay. So sometimes we got from our past math experiences, it's all about getting that final answer. It's like cranking it out. But this is an expression that's totally valid, and that expression represents the volume of the box when the side cutout is 8. Or sorry, 0.5. Okay, totally valid to do that. Okay, so let's talk about functions. Okay, functions are a very powerful tool in mathematics, a of relating, it's a relationship of two quantities, two changing quantities, okay?
So no matter what number you plug in
Yeah.
for x, you'll always get the same answer. Is that true?
So are you saying that the volume is not changing for a changing x?
Yeah, because when I plugged in 0.5 and plugging in 3,
Okay.
both times it came out the same answer.
So if we change, oh jeez.
That's aggressive.
So do we always get the same volume for different cutout lengths? Yes or no? All right, let's look at a really small x. There's a really small x.
It's also super wide.
Yeah, but I can make x even smaller. There's a really super small x. Is that a lot of volume or a little volume? Not very, no, it's not very much because it's super short, right? The height is really short. So compare that volume to say this volume. The same? There's gonna be a lot more. It's gonna be a lot more volume. So did the two that they gave you just happen to give the same?
Yeah.
Okay, so those two, so what happens is you have a very small volume to start out with, and then it increases, and then somewhere along here we're gonna have the largest volume possible. And then as you keep increasing the square cutout, what happens to your volume? It's gonna start decreasing again. So it just happens that those two that they picked, 0.5 was the volume that you get like as the volume increases, and then it maxes out, and then it decreases, and then you got the same volume kind of as it was on the way down.
Okay.
Yeah, and we'll see that in a second. Okay, but functions are relationships of two changing quantities, okay? We know what quantities are, right? Measurable attributes of objects. So now we saw like with the square cutout length and the volume, as you change the square cutout side length, the volume changes as well. Okay, and so that's a relationship of those two quantities. That's a relationship. A function is a way to model that relationship. Okay, function is a way to model that relationship. Okay, so we can think about it kind of as a machine, okay? A machine that takes something and then gives something else. So what, in that relationship, what is the thing that we start with? So is it the square side cutout? Square cutout side length? Or the cutout side length or the volume? What do we kind of start with in that situation? Yeah, we decide a cutout length, right? We start by deciding a cutout length. And then what do? We've got our formula that then determines okay? And then what does that do? That formula then produces a volume. This is the idea of a function. It's giving, knowing what the value of one quantity is, the function tells you what the corresponding value of the other quantity is. And how does it do it? It does it by this, in this case, it does it by this formula. Okay, and so we call that, in that function, we call that the square cutout side length the input. Okay? And then the volume we call the output. So the function is the relationship between the input and the output. Okay, the rule then is what determines the output given the input. So that was that formula that we created. That's called the rule. Okay, that gives the output given the input. Okay, so here's our symbolic way of showing a function. You've seen this before. This f of x, but we really want to understand this. Okay, so let's identify all the parts of this. Okay, the output is the volume. Okay, the output is the volume. Okay, f, just f by itself is the name of the function, what we name the function. So these are going to be important terms because it gives us a way to talk about these. So let's list this. So we got output, name, make a list here. The input, and where does the input show up in this notation here? Well, it shows up in a couple places. It shows up here in this f of x. So the f of x in the parentheses, the x is the input. But then it shows up in the rule too, because the rule is the formula that cranks on that input value to give us the output value. And then we said there's the rule, of course. That's the formula we came up with. Okay, and then the whole thing is called the definition, the function definition. Okay, so the function definition, this is defining our relationship. It's defining the input, the output, the name, and the rule. Because the function definition includes all of that stuff that we've talked about before.
Which one's the rule?
The rule is the formula, the right side.
Okay.
The rule is what you do to the input to get the output. But now when you say f of x equals that, that's then the whole function definition. Okay? This is what we refer to as, over here, this is what we refer to as function notation. You'll have problems. It'll say, use function notation to yada, yada, yada. So that thing on the left is called function notation, f of x. So in this situation, what does f of x represent in terms of function notation? What does f of x, that whole thing taken together, function notation, what does it represent? They're saying volume up here. Agree with that? Some nods. Yeah. So function notation represents the variable output, right? It represents the output variable. Or the output quantity. This is key, okay? Okay, so in this context, then, I'm going to give you some practice. Okay, so I want you to talk through at your tables. When you see this whole expression, What exactly does that mean? What does this, so there's 4 of them. So, what do each of those mean? A, B, C, and D, practice. So this is about speaking it verbally out loud. So each of those expressions, what mathematically do they mean? Go. Okay, but then what does it mean? That's you're just so what does it mean though? As a 1, you're going to get a value. What does that value mean in the end?
So,
Yeah.
so MG, that's not like logarithms where you make the 3 out, put the 3 out.
Nothing but
Okay.
logarithms.
Just
3 times a number.
Okay.
So
Just
3
wanna make sure.
times a number. Okay, where's Courtney? Courtney, tell me f of 2. So that's how we say it. F of 2. What's the meaning of f of 2? Can you tell me?
What's the volume when you put 2 into the x value?
And what does that mean for our situation here? So you want the volume when what?
When x is 2.
Okay, yeah, the square's cut out side length. So that thing f of 2 represents the volume when the square cut out side length is 2. Does it have meaning on its own if I don't put 2 in there and crank out a number? So I could put 2 in here and get a number. Does anybody do that? Oh, good. That's good. Because that's not. Oh, you did it. Okay, that's fine. What'd you get? 56. You got a value of 56. So without computing that 56, does f of 2 have meaning? Is it relevant? Without finding out that it was 56 inches cubed. Is it okay? F of 2, just by itself. Yeah, it represents that volume when the square cutout side length is 2. Whether or not you calculate the volume. That's what I want to emphasize, is that we can use that to represent what value it is without finding the value. Okay, and that's kind of the beauty of function notation. Okay, so let's go on here. So f of 0.3, where is Andrew? You're up. What's f of 0.3 mean? What does that mean?
Well, it's an input, so you would just plug it in for x, and you can solve it.
No, I want to know, what does f of 0.3 mean? What does f of 0.3 mean? That whole notation. Okay, yes, this is what we're. This is the very main point that we're learning. What's your name right behind it? Kendall. Kendall. What does f of 0.3 mean?
The length of the cutout.
It's the length of a cutout. Let's keep going around the table. Who's next to him? Michael. What does f of 0.3 mean?
Represents the output.
And what is the output in our situation? Okay, which is what quantity? Okay, I already asked Alice. Keep going around the table. So who's this right here? Yeah. What's f of 0.3 mean? It's the length of the square cutout. F of 0.3 is the length of the square cutout. No, okay, you guys. So the function notation is the output quantity. Function notation represents or equals to the output quantity when this is the input quantity. All right, so who's dying to say? Rhoda, what does f of 0.3 mean?
That's the volume of the
Okay, so what is x? So you're doing great, and then so don't say x. So what is x? What is that? What is x? So it's the volume of the box when. Right. This represents the volume of the box when the square cutout side length is 0.3 inches. So if you were unsure about that before, be sure. It's the value of an output quantity for a corresponding input quantity. So this is the volume of the box when the square cutout side length is 0.3. Okay. Tell me your name. Michael. What about f of a? What does f of a mean?
It's the volume when the input's A.
Okay, don't say when the input's a. It's the volume. You use the quantities in the situation the whole way through. It's the volume when what? So you changed gears. You talked about the quantity volume, but then you switched into another mode and you talked about input A. So talk about the quantities the whole time. Talk about the quantities the whole time. It's the volume of the box when?
The quantity is A.
Yeah, what quantity is A? TJ.
On the side length.
Start from the beginning.
So f of a is the volume of when the side length is equal to a.
Right, it's the volume of the box when the square cutout side length is 8 inches. It's the volume of the box when the square cutout side length is 8 inches. Now use all input-output language. So let's stay all input-output language. Tell me your name right here. Casey? So can you, all just in terms of input and output, what is that? Yeah, using just the terms of input and output, what would you say f of a is?
F of A is
Okay, right, it's the volume when the square cutout side length is 8 inches. But now, if it were just any function, and it wasn't the box anymore, you just wanted to use terms input and output to describe that. Tell me your name.
James.
James, tell me.
It would be, F of A would be the output, A would be the input.
Right, it's the output of the function f when the input is a. That whole thing is the output when the function is of the function f when the input is a. Okay, how about D? How about D? Right here. What's your name? Right here. Yeah. Right, because you're not facing me.
over there at the screen. For E? Or
For D.
For D? Okay, so D would be 3 times the volume if D was the side length of the cutout of the square.
Yeah, well done. She said it would be 3 times the volume when you had a square cutout side length of B. 3 times the volume when it had a square cutout side length of B. Now E is a little tricky, but we want to put this all together. And this is kind of the usefulness of E shows the usefulness of one thing that's useful about function notation. So when we're going to plug 1.8 in and get the output, and we're going to plug 1.4 in and get the output, and we're going to subtract, and that's going to give us a number. That's going to give us a number. What would that number mean? Who was first? I don't know. We'll go with Noah.
It's represents the change in the volume and the length of the side length of the cutout changes from 1.4 inches to 1.8.
Is that what you're going to say? Yeah. Say it again. Say it louder. Just listen to this.
It's the change in the volume when the side length changes from 1.4 inches to 1.8.
Right, because this is like a final volume minus initial volume, right? The change in a quantity is final minus initial value of the quantity. So our initial side length was 1.4, and our final side length was 1.8. And so we got the final volume minus the initial volume will give us the change in volume. That's the change in volume when the side cutout length changes from 1.4 to 1.8.
As putting down f 1.4.
Okay, that's a great question. Is that the same as f of 0.4?
No,
Why not?
because
f of 0.4 means what?
you had
Oh, what value?
This is a great question. Anyway. Yeah. F of 0.4 is just the volume when the side cutout length is 0.4. It's not the change in volume when you change the side cutout. Okay, so here's what's going to happen.